You know the feeling. You start researching a complex topic, and suddenly the internet swallows you whole. Stick to traditional search engines, and you get highly accurate results. But you also inherit a massive time debt, forced to manually filter through millions of fragmented hits. So you pivot to a generative LLM like ChatGPT or Claude. You get instant answers, but you're now relying on black box reasoning, risking dangerous hallucinations that can derail your work. This frustrating space between slow accuracy and fast hallucinations is what we call the research dead zone. For modern professionals whose decisions rely entirely on verified information, finding a way out of this trap is the single most critical challenge they face today. Right now, surviving deep research requires a duct-taped workflow. You search on Perplexity, analyze PDFs in SciSpace, and manually copy to Obsidian. We call this the swivel chair workflow today. The constant jumping between disconnected apps creates intense friction and cognitive load. Every time you switch tabs, you lose a little bit of context. Quick Search is designed to eliminate this fragmentation entirely. It builds a single, unified pipeline by combining sparse lexical search with dense neural networks. Today, we are going to measure Quick Search's unified approach directly against the fragmented stack to determine if it actually delivers better results. Because a tool's underlying technology only matters if it tangibly reduces the time and effort required for you to reach a verified conclusion. Let's start with the first point of comparison, search retrieval. Standard keyword searches look for exact text matches. Quick Search uses a multi-stage architecture called Stream. The core of this system is an algorithm named WriteFat. It is a heavily modified version of traditional BM25 search scoring. This chart shows retrieval relevance. Standard search hits a moderate baseline. WriteFat uses a Wikipedia-based frequency index to establish term specificity, filtering out fluff before complex AI processing. Then, neural re-ranking kicks in, boosting relevance by 18 to 25% over standard methods. There is a trade-off here. This dual-stage process adds roughly 200 to 500 milliseconds of query latency compared to a basic Google search. Sacrificing a half second of speed is a required trade if you want to ensure your research is built on the most context-aware foundation possible. Once you find the source, you must extract the data. Standard AI bots frequently fail when hitting dynamic websites, complex PDFs, or modern anti-bot walls. Quick Search deploys the tardigrade crawler. It bypasses modern bot detection by falling back on a heavy, isolated Docker-based browser system when standard fetches fail. The raw text is then handed off to a module called Tractor. Tractor fuses multiple extraction algorithms, like Mozilla Readability, and applies over 100 custom site adapters to format the data. This heavy-duty scraping approach achieves a 95% success rate, preserving structural integrity on complex PDFs. Achieving this success rate requires a massive, rigid backend infrastructure that casual tools intentionally avoid to stay lightweight. If an AI cannot flawlessly extract the raw data, any downstream summary it provides will be inherently corrupted or incomplete. Next is the synthesis phase. Standard LLMs provide decent surface-level summaries, but they struggle to extract and connect deep, multi-layered topics across dozens of documents. Quick Search handles this with the Seek Topic module. Instead of basic keyword matching, it identifies complex, domain-specific phrases using Wikipedia-verified edgegrams. This visualization maps the underlying mathematical structure using a double-ring weighted graph. It places primary concepts in the inner ring and supporting context nodes on the outer ring. This structure creates highly accurate conceptual clusters, testing out as 30% more interpretable. The limitation of this approach is that it is heavily optimized for English and rigidly dependent on Wikipedia's specific structural taxonomies. Adopting a rigid but accurate taxonomy is far more valuable for long-term research than relying on a flexible but hallucination-prone chat interface. The final step of the workflow is organizing the gathered knowledge. Typically, users perform this manually in blank canvas apps like Obsidian, spending hours tagging and linking notes. Quick Search automates this using its World module, an infrastructure preloaded with over 240,000 words and 100,000 Wikipedia concepts. This massive local dictionary relies on a prefix-trie data structure to achieve instant lookup speeds. In this system, concepts are automatically linked and mapped together without requiring a single manual tag from the user. By automating this process, users lose the total freedom of a personal vault and are forced to adapt to Quick Search's inherent logic. Trading absolute organizational freedom for automated instant mapping is the only way to truly scale a single researcher's capacity. The overarching question is clear. Is learning and deploying this complex five-pillar architecture actually worth abandoning your current tools? The answer depends on the cost of context, balancing the friction of learning a new tool against the depth of the task at hand. Quick Search is the wrong choice for casual searches, simple factual lookups, or basic summarization. It is absolute overkill for those tasks. It excels when you are tracking multi-hop reasoning over weeks of deep, interconnected research. Adopting it means accepting a learning curve, trusting its specific taxonomy, and tolerating slight computational latency in exchange for precision. Quick search functions as a comprehensive, structured methodology, requiring far more from the researcher than a simple search engine. This flowchart breaks down the final decision framework based on your primary research goal. If you need speed and casual queries, stick to Perplexity or Claude for fast conversational answers. If you want bespoke control, use SciSpace for isolated academic PDFs, or build out purely custom notes in Obsidian. But for unified, heavy-duty research, the central path leads directly to Quick Search as the ultimate destination for complex workflows. While it may be overkill for the average user, Quick Search successfully eliminates the swivel chair problem, making it the premier interface for those who need the internet to function as a self-organizing mind map.
Imagine you walk into a massive Gordy's library to research a crucial project. You are totally focused. But the second you step through the doors, a tornado just rips through the building.
Oh, wow. Okay.
Right. Millions of pages are suddenly floating in the air in this chaotic swirl. And when you reach out to grab just one page that looks useful, a librarian sprints over, slaps it out of your hand, and instead confidently recites a summary they just completely made up on the spot.
Yeah, that sounds like a total nightmare.
It really is. But that, in a nutshell, is what it feels like to research on the modern internet. You either get a million disconnected links thrown at you by a traditional search engine, or you get a perfectly smooth, hallucinated answer from an AI bot that, completely loses the nuance of the original sources.
It is a phenomenal bottleneck for human progress. I mean, we're living in an era where we're just drowning in data, yet we're completely starving for actual structured knowledge.
Yeah, exactly. The sheer volume of information overload isn't just an annoyance anymore. It's the defining cognitive hurdle of our time. You don't just need more information beamed at your screen. You need a reliable mechanism to filter the noise, connect disparate ideas, and actually verify where those ideas came from.
Which is the entire mission of today's deep dive. We are looking at a highly anticipated 2026 research paper by Alex Gohl. It's titled QWKsearch.com Reimagines the Internet as Self-Organizing Mind Map.
It's a fascinating read.
It really is. And reading through the source material, it becomes immediately clear that this isn't just another incremental tweak to a search bar. This is a ground-up architectural framework trying to turn the absolute chaos of the web into a structured, self-organizing second brain for you. So, okay, let's unpack this. Why are our current information retrieval systems failing us so miserably, and why does this specific paper claim to have the ultimate fix? Well, to appreciate the fix, we really have to look under the hood at the exact breaking point of the tools you're probably using every single day. Right now, information retrieval broadly falls into two distinct philosophies.
Okay, two philosophies.
Yeah, first you have what computer scientists call sparse retrieval. This is the classic keyword search you basically grew up with. It relies on algorithms like BM25 to do exact match word hunting.
Right.
It is incredibly fast and is highly transparent. But to be blunt, it is pretty dumb. It doesn't understand context or synonyms.
Right, so if I search for a document about an automobile, the algorithm is literally just playing a matching game with the letters AUTOMOBILE.
Exactly.
It could completely ignore the greatest research paper ever written on the topic if the author happened to only use the word car.
Yeah, that is the fundamental flaw of sparse retrieval. So the tech industry reacted by moving to the total opposite extreme, which is dense retrieval.
Okay, dense retrieval.
Right. This is where neural networks and modern AI come in. Instead of matching letters, the AI translates your words into mathematical vectors in a multidimensional space. It maps the actual meaning of the words. It understands that automobile and car live in the same semantic neighborhood.
That sounds perfect, honestly. Why isn't that just the standard for everything?
Because the computational cost is astronomical. I mean, scanning billions of documents to understand their semantic neighborhood requires massive server farms and just incredible amounts of energy.
Oh, right, the power grid issue.
Exactly. It's incredibly slow and expensive for just a daily query. And ironically, dense retrieval actually struggles with exact term matching.
Wait, really? It struggles with exact matching?
Yeah. If you are a mechanic looking for a very specific serial number for a part, or a doctor searching for a rare, highly specific chemical compound, the neural network might just gloss over it. It's looking for the overall vibe or concept of the document, so it frequently misses the exact characters you desperately need.
So we're stuck between fast but dumb and smart but incredibly slow. But haven't tech companies spent the last couple of years trying to, take these two methods together?
They have, yeah. The massive trend from 2024 through 2025 was a hybrid architecture called ARG. That's Retrieval Augmented Generation.
Right, RG. We've talked about that before.
Yeah, and RG was heavily marketed as the ultimate band-aid for AI hallucinations. The idea was simple. Instead of letting a large language model just guess an answer from its vast, murky training data, the system searches a specific database first, pulls a few relevant documents, hands them to the AI, and dictates only answer the user's prompt based on the text in these specific documents.
It's basically giving the AI an open book test.
That is a great way to visualize it. But here is where the open book test analogy breaks down, and where ROG hits a major wall. Imagine an open book test where the AI is only allowed to read page 4 and page 400.
Oh, I see.
Yeah, RG struggles immensely with a concept called multi-hop reasoning.
Multi-hop reasoning. Break that down for me.
Sure. Suppose you are trying to figure out if a new medication causes a specific skin rash. Document A mentions the medication contains chemical X, but it doesn't mention the rash at all.
Right.
Then document B, from a totally different medical journal, mentions that chemical X causes the rash. A human researcher would naturally connect those two dots. But RBOC frequently fails to bridge that gap because the dots are just too far apart in the data space. It can't hop from one concept to the next to synthesize a new conclusion.
Wow. So going back to our library analogy, traditional search is the librarian who just dumps 10,000 unread books on your desk and walks away. Our Alex is a librarian who reads one paragraph from 2 different books, shrugs, and says they don't know the answer.
Exactly.
What you actually need, and what this QWalk search paper is aiming to build, is a tireless research assistant who reads all 10,000 books, highlights the vital parts, strips out the junk, and then literally draws a map on a whiteboard showing you exactly how all the evidence connects.
This raises an important question, though. How do you mathematically build a system that is as lightning fast as that initial keyword search, but as intelligent and context-aware as the neural AI? And you have to do it without requiring $1 billion supercomputer just to answer your daily questions.
Well, according to Alex School's paper, you can't just take the old systems together. You have to rebuild the very first step of the search pipeline from scratch.
You do. And the Quack Search framework tackles this by introducing a core engine called STREAM that stands for Search with Top Result Extraction and Answer Model.
STREAM. Got it.
The very first thing STREAM does differently is that it absolutely refuses to rely on a single search index. It utilizes a multi-source meta search. It aggregates results across various major search engines simultaneously, all in parallel.
Wait, why is that necessary? Isn't Google or Bing enough of a starting point?
Relying on a single engine introduces a massive blind spot, especially for complex research. Different engines have totally different indexing priorities and proprietary algorithms.
Oh, so they filter things differently.
Exactly. If you are researching a rapidly evolving scientific breakthrough or a highly nuanced historical event, a single search engine might inadvertently censor or bury crucial perspectives. Stream casts a much wider, totally unbiased net from the very first millisecond.
Okay, so Stream casts this massive net and pulls in hundreds of links from all over the web, but now it has the exact opposite problem. It has too much information. How does it rapidly figure out which of those documents actually matter without triggering that computationally exhausting, slow neural network process we talked about earlier?
This is where we get into the math, specifically a proprietary algorithm they call RightFat.
RightFat.
Yeah, this is their engine for scoring relevance, and it's a fascinating piece of engineering. It goes back to that classic fast BM25 formula we discussed, the keyword matcher, and essentially gives it a structural upgrade. Now, the old BM25 formula was useful because it had a concept called term frequency saturation.
Meaning, if I search for the word cholesterol, and a spam website just repeats the word cholesterol 500 times in invisible text, the algorithm doesn't just infinitely boost that page's score.
Exactly. It recognizes that the document is saturated and just stops giving it points. It also normalizes for document length, ensuring a dense 50-page PDF doesn't unfairly outrank a brilliant, concise 2-page article just because the PDF happens to contain more total words.
Makes sense.
So BM25 is a solid foundation. But RightFat supercharges that baseline math by injecting a brand new variable called WikiIDF.
WikiIDF.
Yes, which stands for Wikipedia-based inverse document frequency.
Inverse document frequency. Okay, break that down for me. How exactly does Wikipedia fit into a math formula?
Well, in traditional search algorithms, the system has to figure out if a word you typed is important or rare. To do that, it looks at the specific batch of documents you are currently searching.
Right.
But think about the flaw there. If you are searching a very narrow niche medical database, the algorithm gets a highly skewed, warped view of how rare a word actually is in general human language. It completely loses perspective.
Oh, I see. Because inside that medical database, a super rare medical term suddenly looks incredibly common.
Yes, precisely.
Yeah.
RightFat solves this by using Wikipedia's massive generalized database to establish a permanent, stable baseline for term specificity. It dynamically tunes its mathematical parameters based on the length of your query and the variance in the documents it's scanning.
So it's using the entirety of Wikipedia as a giant anchor to understand how humans actually prioritize words.
Yes.
And what's the actual payoff of this math? Like, does it actually work in practice?
The paper provides very concrete metrics. By using RightFat, the system achieves an 18 to 25% improvement in search relevance over traditional methods. They measure this using a standard metric called NDCG at 10.
Okay, and in practical terms for you, the user, what does that mean?
It means the system is vastly more successful at guaranteeing that the top 10 results you see are genuinely the most relevant, high-quality documents available, rather than just SEO-optimized spam.
I have to push back on this, though.
Oh.
If this entire scoring system relies on Wikipedia to establish its baseline of what terms are important or specific, doesn't it just inherit all of Wikipedia's blind spots?
That's a fair question.
I mean, if a cutting-edge scientific term or a new slang word or a really niche cultural concept hasn't been given a Wikipedia page yet, does the AI just mathematically assume it's garbage and ignore it?
That is a very sharp critique, and honestly, it is a trap that many early AI models fell right into. However, the Qt search architecture actually anticipates this limitation. They didn't build it as a static closed loop.
Oh, good.
Yeah, the framework includes a dedicated mechanism for dynamic vocabulary expansion. As the system processes new documents and encounters novel terms that aren't in the Wikipedia baseline, it learns them. It measures their contextual weight in real time.
So it adapts.
Yes. Furthermore, the architecture allows for domain-specific vocabulary imports. So, if you are a legal researcher, you can import a legal lexicon that just overrides the general Wikipedia baseline. Wikipedia acts as the anchor, but the ship can still sail into totally new waters.
Okay, that makes a lot of sense.
Yeah.
So Stream uses this RightFat math to find the absolute best links, but finding a link is only half the battle. Now, the AI actually has to click the link and read the web page.
And that's where things get messy.
Right, let's be honest, the modern web is a totally hostile environment. It's just a nightmare of newsletter pop-ups, cookie consent banners, auto-playing videos, infinite scrolling, and aggressive anti-bot security. How does the system not just immediately crash when it hits a paywall or a bot blocker?
It is incredibly hostile, and standard automated readers fail constantly because of it. To survive this, Qt Search deploys a custom web crawling infrastructure they named tardigrade.
Here's where it gets really interesting, because the naming here is absolutely brilliant. For anyone who isn't a massive biology nerd, a tardigrade is a microscopic animal, sometimes called a water bear.
Yeah, they're amazing.
They really are. It is famous for being virtually indestructible. You can blast it with extreme radiation, freeze it to near absolute zero, boil it, or even throw it into the vacuum of space, and it survives. It just adapts. And in this context, the developers built a crawler designed to survive the most hostile anti-scraping environments on the modern web.
The water bear analogy perfectly matches the engineering here. Tardigrade operates using a tiered, adaptive approach. It starts simple. It tries to use a very lightweight, incredibly fast fetch API. If the web page is just straightforward text, Tardigrade grabs it in milliseconds and moves on.
Nice and easy.
But if it hits a wall, say the website relies heavily on dynamic JavaScript to render the text, or a security firewall throws up a bot blocker, Tardigrade doesn't just return an error. It seamlessly falls back to a heavy-duty Docker-based container system.
Meaning it changes its approach entirely.
Precisely. It spins up isolated, highly secure browser instances, and to get past the security blockers, it actively rotates its browser fingerprints.
Wait, browser fingerprints?
Yeah. Websites block bots by recognizing their rigid digital footprints. Tardigrade survives by constantly changing its disguise. It swaps out its fake digital fingerprints so the target website thinks, oh, this isn't a bot, this is just a human using a Mac in Ohio. Or, this is a mobile phone in London.
Cool.
It manages proxy networks and maintains persistent cookie sessions just to ensure it can reach the actual text you asked for.
But reaching the text creates the next massive headache, right? If Tardigrade successfully disguises itself and downloads a modern web page, it is downloading a massive mess.
True.
Think about a recipe blog. You just want the steps to bake the cake, but you have to scroll past 4,000 words about the author's childhood, 5 video ads, a navigation sidebar, and a totally toxic comment section. If the AI reads all of that, it's going to get completely confused. How does it know what the actual article is?
That is the job of the next component in the pipeline, which is Tractor. Yeah. Tractor is the text extractor. And rather than relying on a single, potentially flawed method to clean the page, Tractor actually fuses two different highly respected open source algorithms. It uses Mozilla readability and Postlight Mercury.
Oh, I've heard of Mozilla readability.
Yeah, it uses heuristics like text length and link density to guess where the main article lives. Mercury, on the other hand, uses a slightly different set of logical rules.
So it's essentially like having two totally different, highly opinionated human editors arguing over a messy manuscript, crossing out different parts, and then combining their notes to find the perfect final draft.
That's exactly how it functions. By constantly comparing where the two algorithms agree and disagree, Tractor identifies the high-confidence text regions and just strips away all the ads and sidebars. It even comes equipped with over 100 custom adapters for major complex websites to handle their unique formatting quirks.
And the paper mentions it's remarkably good at reading PDFs too, right? Because PDFs are notoriously terrible for AI to parse.
They are, because a PDF isn't really a text document. It's more like a digital photograph of a page. But Tractor preserves the semantic hierarchy. It understands headers, paragraphs, and even those complex multi-column academic layouts.
That's super impressive.
It is. It even integrates logic from an advanced framework called MoE, which is specifically designed to extract citation metadata. It can literally validate authors against a database of over 90,000 academic names. Across standard web content, this dual engine approach gives Tractor a staggering 95% plus success rate in pulling perfectly clean text.
Okay, let's just pause and track the journey so far. You type a query. Stream casts a wide net across multiple engines. WriteFat uses Wikipedia anchored math to score the relevance and find the best links. Tardigrade puts on a disguise to sneak past the website's security bouncers. And Tractor acts as the editor, stripping away the ads and pop-ups to leave perfectly clean text.
Spot on.
We finally have pristine, highly relevant information. But we still just have text. How does the system synthesize that text into the actual mind map the paper promises? I mean, how does it make this digestible for you, the learner, so you aren't just reading endless paragraphs?
The synthesis, the actual mapping of the knowledge, happens in a massive component called World. That stands for Wikipedia Outline Relational Lexicon and Dictionary. World is the underlying knowledge base of the entire system. It stores over 240,000 distinct words and phrases.
That's a massive dictionary.
It is, but it doesn't store them like a normal alphabetical dictionary. It stores them using a specialized data structure called a JSON prefix trie.
A prefix trie. We're getting deep into computer science territory here. Try to visualize that for us.
Okay, think of it like a highly efficient physical filing cabinet shaped like a branching tree. In a normal database, the word cat and the word car are stored as two completely separate entries. Every time you search, the computer scans the whole list. In a prefix trie, the system stores the shared prefix first, the letters C and A. From there, the tree branches off. One branch goes to T for cat, another branch goes to R for car.
So it's not wasting time rereading the beginning of words, it just travels down the branches.
Yes, and because of this branching structure, the system achieves what is known as O of 1 lookup time.
O of 1? What does that mean in plain English?
In plain English, that means the lookup speed is instantaneous, literally measured in microseconds, regardless of how massive the database gets. Finding a word among 10 words takes the exact same microsecond as finding it among 10 million words.
That speed is incredible, but why does a search engine need to map the dictionary that way?
Because it enables a critical feature called noun edge gram generation. By instantly mapping branches of words, the system understands context. It recognizes that the phrase Secretary of State is one complete, meaningful, singular concept. It is not three separate words that just happen to be standing next to each other.
Oh, that is a huge distinction. A basic keyword search would break that apart. It might hand you a document about a corporate secretary and another document about the state of liquid water, completely missing the political office you were actually researching.
Exactly. Once the world component accurately identifies these complete concepts, it hands them over to a module called Seek Topic. Seek Topic's job is to build the actual visual mind map. It does this by generating a double ring weighted graph.
A double ring. So picture a target with a bullseye.
Yes, exactly. In the inner ring, the bullseye, you have the primary concepts. These are the extracted noun edge grams, like our Secretary of State example, or the chemical compound we mentioned earlier.
Okay.
In the outer ring, surrounding the concepts, you have the context. These are the actual verbatim sentences and passages pulled from the source documents that support the inner concept. The AI then draws weighted lines, or edges, connecting the concepts to each other based on their relationships, and connecting those concepts back to their supporting sentences in the outer ring.
Wow. It isn't just listing facts, it is literally mapping the geometry of the ideas. It's drawing the constellation.
What's fascinating here is the unprecedented level of transparency this architecture provides. Think about modern neural networks like ChatGPT. They are black boxes. You ask a question, the AI performs billions of invisible calculations and spits out an answer. You have absolutely no idea how it arrived at that conclusion.
Right, not at all.
But this double ring graph structure is 100% interpretable. You can look at the mind map, see exactly how the AI connected two distinct concepts, and then physically trace the line back to the exact source sentence in the outer ring. The AI is completely showing its work.
Okay, the mechanics of this, the math, the crawlers, the instant prefix trees, they're undeniably impressive. But let's bring it all back down to earth. How does this actually manifest for the user? How does this fundamentally change the way you interact with knowledge when you sit down at your desk on a Tuesday morning to figure something out?
The most immediate application is how this framework integrates with personal knowledge management systems, or PKMs. If you use tools like Obsidian, Roam, or SciSpace, you know they allow you to create your own localized knowledge base using bidirectional links.
Yeah, I love Obsidian.
Right. So when you take a note on a concept and link it, the software automatically creates a backlink showing every other note you've ever written that touches on that same idea.
Which perfectly mirrors how human associative thinking actually works. Our brains don't store memories in isolated manila folders. We think in massive, messy webs of relations.
Precisely. By plugging the key search output directly into these KKM tools, you are effectively offloading the burden of information structuring. You are building a true second brain. The AI handles the mechanical, tedious labor of gathering the data, cleaning it, and drawing the initial lines of connection.
So it does the heavy lifting.
Yeah, which frees up your biological brain's finite cognitive resources for higher level work like creative synthesis, critical analysis, and actually applying the knowledge. You stop being a data hoarder, and you become a navigator of a structured landscape.
And the paper points to a much grander societal vision here, beyond just making our personal notes tidier.
It does. The paper envisions using this structured, objective mapping to untangle complex, large-scale societal debates. For example, the researchers reference testing the system on the MR dataset.
MR dataset.
Yes. This is a massive, multimodal dataset, specifically designed to annotate political debates and public arguments. Now, we must be absolutely clear here. The calc search system does not take a political side. It has no concept of what is morally right or wrong.
Okay, so if it's looking at left-wing and right-wing arguments, it's just a cartographer. It just maps the territory.
Exactly. It maps the structure of the arguments objectively. It catalogs the support and attack relationships between different argumentative units. It outputs a map that basically says, person A claims X. Person B attacks claim X with piece of evidence Y. Person C then supports person A by citing document Z.
So what does this all mean? The paper talks about moving toward a democratized AI economy. If language models and search engines can distill the chaos of collective human thought into a structured vector space where every single point is weighed based on its evidence and connections, you fundamentally change the internet.
You really do.
You start to reward actual logical influence and verified citations rather than just rewarding the loudest, angriest voice in the room. The AI is forced to expose the scaffolding of a debate based on the sentences it actually pulled.
It creates an environment of total transparency. When the AI shows you a conclusion, it provides the exact roadmap of how it got there. It empowers you as a critical thinker by handing you the entire landscape of a debate, completely synthesized, with all the attack and support relationships totally visible.
That's huge.
It is. You can make up your own mind based on structure and evidence, rather than drowning in conflicting, context-free hot takes on social media.
Let's pull all of these threads together. We started with this deeply relatable modern problem of information overload, the tornado hitting the library. We explored how QSearch addresses this by fundamentally rebuilding the architecture of retrieval.
Right.
They employ a hybrid of classic transparent math in WriteFat, anchored by massive Wikipedia lexicons, to understand context without the insane computing costs of neural networks. They deploy resilient disguise-wearing crawlers like Tardigrade and dual-engine extractors like Tractor to pull clean data from an incredibly hostile web.
And crucially, they map that data. By utilizing prefix tries and double-ring weighted graphs, they synthesize the noise into an interpretable, transparent structure. The paper explicitly notes that implementing this system can cut complex research task times by up to 40%. But if we connect this to the bigger picture, it is far more than just a time saver. It is a structural upgrade to how we process reality. As digital information continues to grow at an exponential rate, simply hoarding data or relying on black box AI summaries is just not going to be enough. Adopting tools that structurally synthesize and objectively connect knowledge is going to be the only way for you to remain a critical thinker in the coming decades.
It really is the difference between blindly memorizing an encyclopedia and actually understanding the mechanics of how the world works. Which brings me to a final thought I want to leave you with. Something to mull over as you go about your week and build your own notes. We just talked about how this system can objectively map out the logical support and attack relationships in massive public debates, tracking the exact flow of evidence and exposing the contradictions. Well, if this technology eventually integrates directly into your second brain, your personal Obsidian vault, your own private journals and thoughts, what happens when we turn this relentless logic mapping AI inward?
Oh, wow.
Will we be ready for a tool that silently maps out our own internal knowledge base and actively highlights the logical fallacies, the unbacked claims, and the direct contradictions in our own deeply held beliefs? We wanted a system to clean up the messy library of the internet, but we might just end up having to clean up the messy libraries of our own minds.
That is a profound and, frankly, slightly terrifying prospect to consider.
We will leave you to think about that one. Keep questioning the map, and we'll catch you on the next deep dive.